Now let's take a look at the first black box test technique, which is equivalence partitioning, or EP for short. I guess this one won't take much of our time, as we encountered this test technique a couple of times already. So the concept behind EP is that data are divided into partitions, and all data within the same partition has the same outcome. So if a defect is present in one partition, it's supposed that exercising just one value from the partition will be enough to detect any issues. This means that to achieve 100% equivalence partitioning coverage, we will need to exercise one value at least from each partition, including any invalid partitions. So let's take a look at a practical application of equivalence partitioning. So I use some medications that require sensitive storage conditions. So I want to test if the refrigerator is working as expected or not. So I will refer to the requirements, in this case the storage conditions, documented on the back of one of the medications, which states that the medication should be stored at a temperature between 2 and 8 degrees Celsius. So to analyze this situation in EP, it's always better to draw the partitions themselves. So we have three partitions. From 1 degree and below is cooling off. From 2 to 8 degrees is just the fan to keep temperature homogeneous across the device. And above 9, which requires an active cooling to get the temperature back to the accepted range. To test this device using EP, we can use only one value from each partition. So we can theoretically assume that if the temperature inside the device is 0, 1, or even -4, the expected outcome is off. Similarly, we can think of values like 2, 5, or 8 as values that have the same outcome, which is fan. Lastly, temperatures like 9, 11, or even 3000 belong to the cooling partition. So I want you to analyze the following data sets and choose the one that would achieve 100% EP coverage of this cooling device. Pause the video until you figure out the answer. You have 1 minute. Alright, so let's take a look at the first option. 2, 4, and 8 all belongs to the fan partition. This means that off and cooling partitions are not covered. So this option provides just 33% coverage. For the second option, the values 0 and 1 belongs to the off partition. The value 9 belongs to the cool partition, while the fan partition remains unverified by any value. So this option provides 66% coverage. The last option do provide 100% coverage. We have the values -6 covering the off partition, 2 covering the fan partition, and 9 covering the cool partition. As you can see, visualizing the partitions makes things much easier. So if you encounter a question with no partition sketched, it's better to draw it so you can see the full picture and answer the question easily. Now let's take another equivalence partitioning problem. So we want to verify an app that calculates the tax according to the income. The app can accept any numeric value, and it serves the function of calculating the amount of tax. So a person with an income from 1 to 1000 will not have to pay any taxes. Above 1000, up to 5000 will pay 5% of his income as tax. And above 5000, they will have to pay 10% taxes. So you are required to extract the right option that achieves 100% EP coverage with the least amount of data. So as usual, pause the video, sketch the partitions, and you can take 3 minutes to answer this one. Alright, let's take a look at these options. And I hope you have sketched the partitions like this. If you have identified 3 partitions only, it means you have probably forgotten to include the invalid partition. Remember, the app can accept any numeric input. So practically, there is nothing that can prevent the user from entering 0 or any negative number. In this case, we need to verify that the app responds correctly by, let's say, popping a message telling the user that the minimum accepted amount is 1. Now that we know that we have 4 partitions, let's check the options to see which of them achieves 100% coverage with minimal data to test. So option 1 and 2 are definitely not the correct answers, as each of them contains just 3 values while having 4 partitions. So it's impossible that any of these options can achieve 100% EP coverage. Now option 3 has the following values: -5, which covers the invalid partition, 100, which covers the no tax partition, 5,000, which covers the 5% tax partition, 5,001 and 7,000, both covering the 10% tax partition. So I guess that option 3 is the correct answer, as it achieves 100% equivalence partitioning coverage. But option 4 also achieves 100% coverage. But why we didn't take it as the correct answer? This is because we only need 4 values for achieving 100% coverage. And the question stated that we need to select the minimum number of values that achieve the required coverage. And while option 3 provides 5 values, option 4 provides 7 values. So option 4 will need more time and effort to achieve the same outcome as option 3. So I guess this wraps equivalence partitioning for now. So as usual, take care, and I'll see you on the next one.